Okay, so hello everyone. Today I'll be taking you through one of the most important algorithms in graph theory, which is PRIM's algorithm, used to find the minimum cost spanning tree or MST. We'll go through the definitions, concepts, and real world uses. So the introduction, this is the concept of the spanning tree. A spanning tree connects all the nodes of a graph without forming any cycles. Among many possible spanning trees, the minimum spanning tree is the one with least total edge weight. Historically, MSTs were used for planning efficiently uh, utility lines, basically to plan efficient utility lines. Today, they're everywhere from network cabling to transport routes to machine learning. So before we go continue on, we learn some basics and terminologies. So a graph is just a set of points connected by lines. If there are no, if the graphs have no direction, it's called undirected graph. Like the image you see here is an undirected graph. If there's a way to get from any node to another, it's a connected graph. If the edges have numbers attached to them, they are weighted graphs. The spanning tree includes all nodes, avoids cycles, and aims to minimize the edge weights. So basically, we have two algorithms for MSTs. One is the Kruskal's algorithm, which works edge to edge. Second is the PRIM's algorithm, which expands from the starting node. Today, our focus is on PRIM's algorithm, uh, which is especially efficient for dense graphs. Okay, now moving on. So the PRIM's algorithm, to give us an overview of the PRIM's algorithm. The PRIM's algorithm is a greedy algorithm. It builds MST step by step, always choosing the smallest available edge that adds a new vertex, starting from any node and repeat until all nodes are included. Its time complexity ranges from O to the big O to V square for the basic version to big O E log V if you use a priority queue. Now, so let's just go through an example problem. So we have basic five graph vertices here, which is A, B, C, D, and E. You can see the edge weights are marked alongside this. So now we will start from the smallest vertex, which is vertex A. So now we can choose the from basically we're trying to make it to the next vertex in the least possible weight. So you choose A and B, which has a weight of 2. Then from B, you can either choose B to D, which is 4, or B to C, which is 1. The smaller one is clearly B to C, which is 1. So you choose B to C. From then, you choose B to D, which is again a weight of 4. You could have also chosen C to D, but since that is a weight of 5, which is more than 4, we are not choosing that. And then in the very last one, we shall choose C to E. Since it is the lesser option from of considering 7, we do that. So doing in such a way, we find the minimum spanning tree. So you'll see the total cost is 2 plus 1 plus 4 plus 6, which is basically the weights added together of our PRIMS algorithm output. So which is comes to 13. So now we have a pseudo code for the PRIMS algorithm. So at the start, the step one is basically just initialization. We begin by defining the function. This will take the graph as input, specifically a list of nodes and their connected weighted edges. Now initialize a MST with one arbitrary node. This means that we can start from any vertex. Let's say we pick vertex A at this point, only A is our MST. Step 2 is the main loop. So while the MST does not include all nodes, we now enter a loop that keeps running until all nodes are added to the MST. With this loop, the core task is finding the minimum weight edge connecting to the MST to a new node. This is the greedy step. From the MST, we look outward or edges and pick the smallest one that connects the node we haven't included yet. Then add the edge and a new node to the MST. That edge and its destination now become a part of the MST. Uh, So let's expand on what's written here basically. So to implement this more efficiently, especially in our code, we use a priority queue or a mini heap. So initialize the priority queue, which is q, start from any variable v. At the start, we add all edges and our starting vertex priority remains at q. While q is not empty, this loop continues until all edges have been explored until the MSB is complete. Inside the loop, extract edge with minimum weight. We remove the smallest weight edge from the queue. Then, if the node at the other end is not visited, we'll mark it as visited and then add it to the MST and add all the edges from this node to queue. We check whether the destination of that edge has already been visited. If it hasn't, we mark it as visited. Then we include it to the edge, and most importantly, we add all this to the new node's outgoing edges into the priority queue to be considered next. So basically, Prim's algorithm builds the tree one node at a time, always choosing the next lightest edge, ensuring we get the minimum total weight without cycles. This pseudo code is both elegant and practical. It scales well with graphs using the right data structures, especially with heaps and adjacency lists. Now we shall move on to another problem. So here is another practice problem. I recommend Prim's algorithm and try solving this yourself. It's a good exercise to get familiarized yourself with the Prim's algorithm. Here I have not mentioned the steps. I have only mentioned the MST edges and the total cost. The step-by-step is given in the diagram you can see. Try solving this on your own. Now here we have another practice problem. So this is also a similar problem as the previous one. It's just a different case. It's an easier problem. Try practicing this on your own as well. Now we have edge cases and limitations. So Prim's algorithm only works on connected graphs. If the graph is disconnected, that is you can't form a single spanning tree. Also, it handles negative weights well since it always picks the smallest edge. It doesn't rely on assumptions about the positive values. So compared to Kruskal's and Prim's, Prim's is better for dense graphs while Kruskal is better for sparse ones. Now, if we go into the details of it, it basically says that Prim's is a greedy algorithm that finds a minimum spanning tree for a weighted undirected graph, while Kruskal's is a minimum spanning tree algorithm which finds the edge of the least possible weights that connects any two trees in the forest. So it generates the minimum spanning tree starting from the root vertex, generates the minimum spanning tree starting from the least weighted edge. So here in Prim's algorithm we always start with the vertex which has the least weight, while in Kruskal's algorithm we check where any node that has the most number of connections and the least weight. So selects the root vertex selects the shortest edge. That is basically the difference between Kruskal's and Prim's algorithms. Now, real life applications of MSTs. So, in network designing, so this is one of the most common applications. So, imagine you're setting up a network, say for an office building or a college campus. You want every computer or router connected, but with minimum amount of cabling. Using an MST, you can determine which connections to make so that every device is connected, the total cable length or cost is minimized, and there are no redundant loops that could complicate routing. This applies to internet infrastructure, LANs, and even tower layouts. Secondly, we have transport networks. So think of a road, railway, or subway systems, cities you want to connect to all your locations, but without spending money unnecessarily. Using MSTs, urban planners can decide minimum cost road layouts that still keep all regions accessible, rail links that connect all cities in a region using fewest tracks possible, or even emergency excavation routes with a minimum travel distance. Uh, Again, we have utility networks. Power grids and water distribution systems are another perfect example. You need to connect every home or substation to the main supply line, but you want to avoid wasting wire or pipe. As an MST will tell you, the most efficient way to lay down cables and pipelines, and also will also ensure complete coverage with minimum material use. It is especially useful in rural electrification projects and renewable energy layouts like solar farms or wind turbines, etc. Now, clustering in machine learning, MSTs aren't limited to physical systems. In supervised machine learning, particularly clustering algorithms like single linkage hierarchical clustering, MSTs are used to group data points. The MST is built over the data and the edges are removed to create clusters of related items. such as grouping customer behavior or image segmentation. The fifth one is approximation algorithms. So MSTs help with solving hard optimization problems like the traveling salesman problems. Although TSP, which is the traveling salesman problems, is hard, you can use an MST to get a near optimum solution efficiently. This kind of solution is widely used in logistics, delivery routing, and circuit designing. So to wrap up, uh, whether it's laying cables, designing roads, or grouping data, or solving hard problems, MSTs are incredibly versatile. They're powerful examples of how a simple graph concept can be applied to complex real-world systems. Now we have a summary. So to summarize, MST connects all nodes at a minimum cost. PRIM's algorithm builds the MST at one node at a time. We saw how to apply it step by step. It's efficient, especially on dense graphs, and it's widely used in the real world applications. Now, for any of you who still have doubts during these problems, let me explain it step by step. So, we have the question layout at the top of the diagram given. So, the first one is we're selecting A to B, which has a weight of just 1 since it is the smallest weight. So once we select that, we will go to B. From B, we have two outgoing edges. One is from B to D, which is a weight of 6. The other is from B to C, which is a weight of 1. So since 6 is more than 1, we're going to take 6. Now we have ABC connection set up. From C, we have edges to B, to D, and to F. Here we can check the lightest one, which is B, but then it's already covered, so there's no need for that. The second lightest one is D, which is the weight of 4. So when we use that. So now we have A, B, D, and C. So after all this, we will check the weight from D. So from D, we have nodes going to C and to E. Since the node to E has a weight of only 2, we'll connect that. Now we only have one vertex left, which is F. Now comparing the lowest energy paths for the things, we'll see that C to F is 7 while E to F is only 5. So therefore we shall take the final one, which is E to F. So we'll get the final answer for our PRIMS algorithm. Now in the second exercise, you will see that if we start from the vertex 1, we have two edges, one going to 3, one going to 2. You will see that the one going to 3 has a weight of just 1, so we'll begin with that. And then from 3, we have a bunch of vertices edges going to 2, to 5, and to 4. But since our aim right now is to go to 2, the smallest way to 2 is not from vertex 3, but rather from vertex 1 itself. So we again go from vertex 1 to vertex 2. Here we go to from 3 to we go to 4, which has just a weight of 2. And now in the final step, we have to connect it to vertex 5. The smallest weight for vertex 5 will be from 3, which is a weight of 4. So when we add all these together, we get 3 plus 1 plus 2 plus 4, which is 10. And this is how you solve a PRIMS algorithm problem. Alright, thank you everyone for watching.